So in the lecture so far, I've pointed out a few times, I know I sound a bit like a broken record, that there isn't currently a canon of machine learning. There is no standard textbook that everyone follows and it just contains all the stuff you need to know. That's because the field is still evolving so fast that pretty much no one can keep up with writing a book and keeping it up to date about the topics that are currently relevant. Those who try to keep up actually are occasionally able to write books, but then even those books quickly date out. So in a course like this, every single time we teach it, and by we I mean for this course, my colleague Jakob Macke and myself who take turns taking these classes, we have to reflect on what we are probably supposed to teach you, what should be the canon actually. Because there is no one out there to tell us, we have to do it ourselves. So we are here, you're sort of live seeing a development of what the canon of machine learning is in 2025. And for me, a sort of strategic decision I've taken when designing this class this term was to say, let's use the idea of computer science design patterns as a guiding principle, a piece of like thread that we can pull ourselves along across the term to identify ideas that have historically been relevant and that are likely to stay relevant even as the field progresses. That's why I keep showing you Python code, for example, why I keep stressing this development of like self-contained pieces of code that we can then call to point out particular patterns that are important and that automate processes. And they stand in, that's the second important strategic decision, for these sort of more fast-moving ideas that you know from other lectures. So I'm trying to make occasional connections to the words you may have heard in a deep learning lecture or in a statistical machine learning lecture or in other machine learning lectures. Later on in the course, I'll make this connection more explicit. So far, I maybe haven't done it enough. So what have we done so far? In this first part of the course, the last, I don't know, 6, 7 lectures or so, we spoke about Gaussian distributions. And we discovered that they have two very interesting aspects that we can use as patterns of thought for what we're doing when we're learning things from data or from mechanistic knowledge. The first one was an active part, a question about how to collect information. That was the story of linear algebra. Gaussian distributions, or conditioning Gaussian distributions, is directly connected to the idea of solving systems of linear equations. And so when we think of solving a system of linear equations as a way of collecting information, as a way of collecting data, of collecting views onto the data, we're effectively designing base classes of data loaders, of active learning agents that follow a policy to collect information efficiently. And they do this by constructing linear combinations, so weighted sums, views onto the data set. And I admittedly kept the connection to deep learning a bit vague because this early on in the course I hadn't even gotten to talk much about deep learning yet. We'll come back to that. Then, in a second phase of this block, we use this Gaussian mechanism in a less active fashion. We sort of called these underlying active algorithms, called linear solvers, to learn a particular type of object, namely functions. So functions are obviously a very important concept in mathematics, relationships between inputs and outputs. And we encountered the Gaussian mechanism as the Gaussian learning, the Gaussian inference process as a very powerful tool to quite generically describe the process of learning a function from data. First, we did this with parametric models, with models that look like this. And I there already made a connection now several times to deep learning. We discovered that learning such a model, which means doing inference on W, using a Gaussian prior on W and assuming a Gaussian likelihood on the observations that are values of the function corrupted by Gaussian noise, amounts to, so first of all, that's a closed form operation. We know how to do it efficiently. It's a simple call to a method of our Gaussian class. And we've discovered that it amounts to finding the best fit for what you might call a shallow neural network. So a neural network that has a single layer of features and then an output layer that constructs a linear combination of these features. We actually also spoke about how to optimize such models, how to find good choices of the features. And that's effectively our first instance of deep learning. From the Bayesian perspective, you do this by maximizing evidence, minimizing negative log likelihood of the data, marginal likelihood of the data. And then we had this fun observation that it's actually possible to extend these models to infinitely wide neural networks, networks that track an infinite set of features if the space of features has some regularity. That maybe also hints at why deep learning might still be a good idea, because we can't just do this with arbitrary choices of infinite sets of features. We have to assume that they have some regular structure. And that's called the kernel trick. Underlying model classes are called kernel machines. And we've now spent 2 or 3 lectures playing around with them. We did a concrete example. We talked about the theory a little bit. And we'll leave it at that for now. And we might come back in maybe next Tuesday on the side. I'll sort of mention that we can actually also condition these kind of models on more scientific information, not just on observed data, on floating point numbers on the disk, but on structural information, on things like differential equations, symmetries, conservation laws, descriptions of nature in a compact form. But today, I'm going to open up a new chapter of the course that will take us to, let's say, a new data type that we want to deal with. So far, the object in question was a function. If I give you pairs of inputs and outputs, and then I give you a new input, predict the next output. That's supervised learning regression, right? Learning a functional relationship. And by the way, so it's actually a little bit more specific. The function classes we've considered so far are only functions that map from an arbitrary space to the real line, so they're real valued functions. There will be an opportunity later after the Pentecost break to point out that we can do something about the output space and learn other types of outputs, if you like structured prediction or classification and various other types of predictions. And then later on, just as a quick outlook so that you don't lose the interest in coming back to the course later, after the Pentecost break, we'll talk about more design patterns. In particular, a few things that I'm personally looking forward to are patterns for learning probability distributions. So if you like generative models, basically. But there will be a really interesting kind of structure to think about from the computational perspective. Then I'll talk actually for several lectures more about the connection to deep learning in more detail. There'll be some very rich language connecting deep neural networks to Gaussian processes, borrowing some concepts from differential geometry. And then towards the end of the term, we'll talk about randomness for a little bit, which I'll mostly be very cautious about, and about relationships between data, structure, imposing structure in an unsupervised fashion in data, and that will lead us to the idea of attention, but it'll bring us also back to lots of historical perspectives. Okay, so now, time series, sequences. That's the next thing we want to talk about. I'll do this in several steps. Today, we'll address the notion of sequences, of learning time series, in a very abstract fashion. Advance warning, this might be, again, one of these sections where you don't like what I'm doing so much, and some of you will say, that wasn't so great, and only a few will be in the green corner of the feedback. And then on Thursday, if you bear with me and join us again on Thursday, I'll talk much more concretely about an actual algorithm that you can actually implement and play around with also in your exercise sheet and your homework. I will stay quite abstract today because it turns out that there is a really interesting algebraic structure that we can leverage for data sets that have temporal structure, which doesn't actually require Gaussian assumptions yet. And so I want to deliberately point those out before we build concrete algorithms. Sometimes it's valuable to stay high level as much as possible before you actually go to a concrete algorithm, because it tells you how general your ideas are. So why do we need to do this in the first place? I showed you a few weeks ago Andrei Kolmogorov talked from his seminal book in the 1920 what something. I forgot the link up there, but you had it in the previous lecture. he points out that actually the main thing we should actually think about when we build models using probability measures is dependence structure. And actually, early versions of this course a few years ago, if you would have taken this course 8 years ago or so, I would have had a lot of focus on conditional independence structure. We would have drawn a lot of graphs and directed graphical models and talked about notions for these graphs and languages on how to talk about them, how to operate on them. This has sort of fallen a bit historically out of fashion. It sort of feels now a bit more like classic AI, so I'm not doing that so much anymore, although the theory is still there. But since the 1920s, people have realized that it's really all about keeping track of independent structures if you want to build something that you can actually use. So fundamentally, the reason for this is that probability theory, while generalizing classic logic, as I pointed out in the very first lecture, is a very powerful notion. This generalization of logical inference that allows us to do inductive reasoning, which is a very powerful idea, unfortunately leads to a drastic increase in computational cost. Right, so if you think of even a binary system, if you think of a set of variables, let's say n variables, that each can take one of two possible values, binary values, then storing a best guess for the value of this binary string has a memory complexity of n, obviously, right? I just need to store n bits, right? But if I want to keep a probability distribution over their possible assignments, then how much do I have to store? Yes, 2 to the n. And more generally, if they don't take just two values, but if they take k possible values, then I have to store k to the n possible hypotheses, right? So there's an exponential increase in cost if we assume that everything can happen. Right? If you want to keep track of every possible hypothesis that could arise, then you get an exponential increase in cost. But if you assume that some of these variables are independent of each other, then you can separate them into subgroups, and you get an exponential decrease in cost. And so by assuming independence, by assuming that you don't have to keep track of basically a full array of possible options with k by k possible combinations, and replacing it by an outer product of something with much less in here degrees of freedom, you get an exponential decrease in cost. And so how does this relate to the models that we've now used so far? This is a very abstract statement. Well, so far in our regression models for using this sort of Gaussian mechanism to do regression, we actually didn't really constrain the capacity of the model. Actually, we did a little bit when we used parametric models. So here is a sort of pictorial view using one of these classical graphical ideas to talk about regression with parameters. So if we're talking about a setting where the function can be described as a sort of a finite set of features times weights, right? That's the situation here. We make a bunch of observations. We have a name for the number of observations. I don't know, like whatever many observations we make here. Then our assumption is that when we condition on the weights, if you think of the conditional distribution for the f's given the w's, then they are independent of each other. So that's an easy thing to keep track of. But when we condition on data, on these terms down here, then we have to keep track of a joint probability distribution over all of the w's. And even if you do this in a Gaussian fashion, then the complexity of doing this is that complexity of linear algebra. So it's, in worst case, cubic in the number of parameters in the size of w in computation and quadratic in memory, right? Because we have to keep track of pairwise interactions between w. The whole situation gets even worse if we think of Gaussian process regression. So when we did non-parametric regression, models that describe function values directly relating to each other without appealing to some latent set of parameters, then we have to keep track of all the possible covariances between all the individual function values at each training point. And in fact, if you want to make predictions, then the prediction points enter the situation as well. So the complexity now of doing inference, of doing machine learning in a model like this, even if you make purely Gaussian assumptions all across the entire problem, so if you assume a Gaussian prior on f, Gaussian independent likelihoods on the y's, linear relationships between y and f, so if you make our life as easy as possible, then we still have to keep track of covariances between all the possible function values. That's a densely connected graph. And because it's linear algebra, the worst case complexity of this is, again, quadratic in the number of function values. In this case, that's the same as the size of the data set in memory, so quadratic memory requirements, and cubic in compute, because we have to do matrix inversions or matrix decompositions. So that's okay. Maybe it's still polynomial, right? So if you're like a theoretical computer scientist, you would say, it's in P, whatever, it's done, right? So it's still feasible, but this is only feasible for certain types of applications. So if you have a data set that, like the example we did, contains something like 1,000 data points, then you can get away with a model like this, right? Maybe you can wait for a few seconds for your machine to do the linear algebra. You can maybe scale to 10,000 data points if you have a very powerful computer. If you have more than 10,000 data points, then you will eventually swap to a model like this with a bunch of the finite set of parameters. Then the cost will be linear in the number of data points and still cubic in the number of parameters that you keep track of. But that still means that the model has sort of a diminishing capacity to make use of incoming data. If you are in a setting where you get an unbounded number of data points that keep arising across time, then you might convince yourself that you need a different type of data structure that allows you to keep capacity around that doesn't diminish as the number of data points keeps growing. And the typical sort of application for this, which is actually more of a description of an idea, is that of a time series. So a situation in which you have an incoming stream of data that keeps arriving in a constant, at a constant rate. So here is an attempt at a definition of what I mean by this. It's not a particularly clean definition. A time series is a sequence of observations that are indexed by some scalar parameter from an ordered space. So from the real line, in general, because you can embed any ordered space in the real line. In particular, we might assume that the time points are equally spaced, that they come at some kind of regular rate, but that is not particular. It's not necessarily required. We could have varying distances between the time points, and then there is a bit of a separation between how we think about t. If we think in the most general sense of t as a continuous variable, then these are called continuous time models. If we think of them as arriving as an countable set, then we might call this discrete time processes. So first of all, maybe important is the word time here, of course, should be understood to be a sort of a metaphor. Right? It doesn't necessarily have to be physical time. It could also be an ordered space in some other nature. But the typical application is that you can think of t as some kind of time. Maybe actually our space-time time. Right? Typical applications for models like this are written down here. I've come up with a few ideas. Imagine you're doing a climate or weather prediction. So if you're, for example, working for the European Center for Medium-Term Weather Forecasting or for the German Weather Service, then you might want to build a software tool that at any point in time allows people to take out their phone and look up a nowcast, right? A prediction of the next hour or 24 hours of the weather, and that process should be running continuously across time. It should never saturate. If you're doing regression with one of the models that we did in previous lectures, then that's not really going to work. If you use a Gaussian process model, a non-parametric model, then eventually you'll run out of compute because your compute cost will grow non-linearly with time. And if you use a parametric model with a bunch of finitely many parameters, then you're fundamentally limited in the capacity of your model. So you will somehow over-constrain your model at some point, and it won't be able to adapt anymore. Another setting, actually typical settings, are ones where compute is in some other ways limited because you're working in an embedded or mobile or edge type application. So if you're building sensors that are running in a car, it doesn't even have to be a self-driving car, right? Just some simple, the sort of stuff that modern cars already do, constantly watching out into the front, checking the distance to the next car or something like this. You want to have a system that never kind of gets stiff, right? That always keeps capacity for new data, medical applications, and so on and so on. Stock prices, financial modeling, and so on. So the setting here is sort of, I wrote a little picture here as well for like as a symbolic type of setting where you keep drawing from a sensor across time, and you want a model that never runs out of capacity. Okay, so to build such a model, we need an idea for a pattern in the language of probability theory that creates a finite memory capacity that is sort of handed on a long time and is kept being used in an efficient fashion. So let's see if we can think of a structure like this. And I'm really going to try and like focus on the structural assumptions so far, not on the concrete instantiations of the probability distributions. And the pattern for this is called a Markov chain. And it looks like this. So we will assume that there is a sequence of things that happen, and that at any point in time, there is a finite object that is called the state. It's called X. And something happens to that state from one time step to the next. But the thing that happens in a local fashion. So that means in code, there's going to be a function f that takes your current state and then returns the next state. So here's an example of such a function. It takes in an old state and a source of randomness, and then it produces a new state. And it does that by adding something to the old state. The important thing is that this function depends as an input only on its direct predecessor, not on everything in the past, but only its direct predecessor. That's the first thing that we need to think about. This is called a transition model, this f. And the notation f is canonic, so I'm going to call it keep calling it f, because everyone in this field, in this subfield, which is, by the way, also called signal processing, uses this notation f. And then something else can also happen, which is at time t, some stuff can happen that only depends on the local state, and that stays basically where it is, right? Whatever happens at t stays at t. So for this, we assume what is called an emission model, or an observation model. That's usually called H, that produces some local stuff, typically something you can see, because if it's something you can't see, then you don't really care, right? Something might happen, but okay, you could predict what might happen locally, but the typical setting is that you observe something locally that you assume has something to do with the stuff that you would like to know about the state. And here the assumption is, again, that the stuff that happens locally depends only on the local state. So this function x, again, does a similar thing. It sort of adds some random noise to it, right? And then we append this x to some list, and now we have a list of states, right, that we can generate. This structure, so this local structure, clearly has something to do with dependence, right? The entire point here is that these functions have a signature that say, to get from one time point to the next, I only consider the current state, and to create the observation at one time point, I only consider the local state. This idea goes back to this Russian mathematician, Andrei Markov, who wrote, actually, interestingly, he only published in Russian. He was a bit, he wasn't particularly internationally well known. He wrote this this treatise for the Society of Physics and Mathematics at Kazan University. So he was very much sort of a local person, called The Generalization of the Law of Large Numbers to Variables that Depend on Each Other. And we wouldn't probably not know about Markov, and we probably wouldn't be calling it Markov chains these days if it weren't for Andrei Kolmogorov, who actually translated his works into, I think he translated those directly into English, actually, and basically informed the rest of the world and said, this is important work, you should read about it. Why? Because it uses this idea, it studies this idea of conditional independence in a very interesting generic case. So before we talk more about how such models can be utilized and how they allow us to save time, compute time and memory time, I want to make a connection to the stuff that we've done earlier in the course so that you sort of, stay on top of things. So I've shown you pictures like this during a regression, right? One-dimensional functions that behave in some way. And this is actually a very concrete case. This is this discretized version of the Wiener process with stepwise perturbations that you may remember. And now, actually, maybe I didn't stress enough in the previous lectures that all the stuff we did in previous lectures didn't really assume much about x, the x-axis here, the input. It could just be pretty much anything, including higher dimensional spaces. But many of the examples that I showed you, of course, were actually in one-dimensional spaces. And so here, we could actually rename the x-axis into the t-axis and say this is across time. And you can think of this as a temporal process, right? And in fact, it actually also happens to be a Markov process. It is exactly of this structure. So because what happens here is actually exactly the kind of code that I just showed you, right? So to get from one time step to the next, we can think of this input space as a discrete set of steps where we index the number of steps literally by an integer, 1, 2, 3, 4, 5, and so on. And at every time step, what happens is that we take the value of the function at the preceding time, and then we add a Gaussian perturbation. And then we keep going, right? So this process actually is an instance of such a time series. But it's just one, and maybe the most basic instance of such a time series. In fact, it is in some sense the generator of a large class of very interesting models called Gaussian Markov processes that we will talk about on Thursday. But there are other instances of such processes that are a bit more complicated. We encountered one already. Here is this ReLU process, if you like, that Grace Waba studied in her work, which also has a continuous time limit, right, with infinitely many features. This is the cubic splines that you may remember. So here I chose some other set of features, so these ReLU features, right, where one after another gets switched on at each point in time. And now let's maybe think about this for a second. What actually happens here is that at every time step, a piecewise linear function gets activated. A way to think about this is to say there is some latent state that maybe doesn't consist anymore of a single real number. I can't quite represent it as a single real number, but it consists of two single numbers, if you like, namely a value and a derivative. And then I can, at each point in time, say what is the current derivative of this function, because it's a piecewise linear function, and what is its current value. And then when I say locally what happens, and well, locally I'll get a change to the derivative that then creates a change to the value in the next state. And then it turns out that I can still do basically the same computation as in this simpler example here. I just need to keep track of two numbers rather than one. So this is maybe it gives a first inkling of, I'm going faster now. So gives a first inkling of how intricate these processes might actually be, these Markov processes they're actually called. They actually allow us to model something a little bit more complicated than just adding something at every time step. But it's a little bit like adding something at every time step. It's a more general idea. So before we can think more about this general idea, a final thing I need to do is to introduce a little bit new notation. So I would like to ask you to flush your memory from the previous lectures about notation. So far, we've talked about functions that map x to y, right? Where y is the output and x is the input. Now, we're going to think about states called x that evolve along time, called t, and we make local observations that are related to the state, and they're also called y. So now the thing we're interested in will be called x. So far, the thing we were interested in was called f. It was a function of x and produced y. Now we're interested in a thing called x, called the state. We get observations called y, and because we are in an ordered space, we're thinking a little bit less, like the role of the input gets a bit easier. It's still around, it's now called time, but it's actually just an index, typically a countable set of indices that come from this ordered space. These models are called state space models because exactly of this character. And the one structure we're now going to leverage is this locality structure called the Markov property. Who's heard of the Markov property before? Everyone. Good. So I don't have to, almost everyone. Like 5 people didn't raise their hand. So for everyone, quick reminder, we're going to talk about it now for the next half hour. As such a collection of states across time will be called a Markov chain if it has the property that its probability there's such a collection of random variables. That's, of course, the important bit, right? We're going to use random variables again in probabilistic machine learning. A collection of random variables which are, with a joint probability distribution over them will be called a Markov chain if it has the property that the conditional distribution for the ith state, given all its predecessors, is given by the conditional distribution or equal to the conditional distribution for the ith state only given its immediate predecessor. So that's the formal description of this locality structure. To predict the next thing, you only need to know where you were immediately coming from, and everything else in the past is shielded away. And it turns out that this structure alone, along with this local observation structure, that observations are only produced in a local fashion, actually is enough to create an algorithmic structure that runs in linear time. That's the entire thing. And what I'll now do, with advance warning that it's going to be a little bit mathematical, is to construct this relationship. And that process comes in signal processing under the name of filtering and smoothing. Who's heard of filtering and smoothing before? Half of you. Who's heard of the Kalman filter? It's the same half. Who's heard of smoothing? Like 10% less? Good. Okay, so that means about half of the room knows this. Well, but you might know a concrete instantiation. Who's heard of the Chapman-Kolmogorov equation? One person. Okay. The Chapman-Kolmogorov equation, which we're now going to construct, is the general version of the filtering pattern. And we'll do that now in this ugly slide. We'll spend some time on it. And the reason, so first of all, here, because it's such an ugly slide, I want to point out why I'm doing this. I realize that every time I do this, people are like, ugh. The point here is we're going to find an algorithmic structure, an abstract operation, a functional relationship that we can generally apply. And the Kalman filter will be the base case of it. But there are much more general frameworks that use the same structure. They are called Bayesian filtering and smoothing. And they are related to other model classes that you may have encountered also in deep learning, like RNNs, for example, right? Recurrent neural networks, or hidden Markov models, and so on and so on. So it's, in my opinion, worth doing this derivation because it highlights the structure we're leveraging without all the fancy linear algebra that shows up when we do Kalman filtering. So how does this work? We are going to make exactly these two assumptions that I mentioned. So we're assuming the Markov property, that's this. And we also assume that observations y are purely local. So that means the probability, the conditional distribution for any individual observation at time t, given all the latent states, factorizes such that it depends only on the local state. If these two things are true, we can do the following thing. We can think about something that is obviously of interest. So that's a predictive distribution for the state at time t, given all the previous data points. So we're moving through time. We have seen some stuff in the past. What do we need to do to keep track of the stuff that we've seen in the past at the local point in time? We do that by doing a little bit of probability theory. So first of all, we reintroduce all the other variables, state variables x. How do we do that? Well, we do this using the sum rule. I said in lecture 1, the sum rule is the trick to get rid of variables you don't want to have in your equation, or to reconsider variables that you now need to think about that you so far didn't have in your equation. So we're expanding the set of things we think about into all the states. Capital X is now a collection from x0 all the way to, well, into the future actually, in like up to time n, if you like. We divide by a 1, right? So this thing down here is just a probability distribution, so it's just divide by 1. Now we're going to expand. So first of all, here we're using the product rule. So we're writing a joint distribution as a product of one side times a conditional, right? So p of x and y is p of x times p of y given x. And we do this both in the numerator and the denominator. Now we think about the fact that our state x consists of these instantiations at various points in time. And so we write them out explicitly. There is x0, x1, x2, x3, and so on. And we just use the product rule. So far, there's no Markov thing going on. We're just writing p of joint x as p of x0 times p of x1 given x0 times p of x2 given x0 and 1, and so on and so on. And we expand this across all the time points all the way up to t. And actually here I could have also expanded it all the way up to beyond t, but I'll do that one line below. Doesn't matter. It's going to cancel out right away. That's it so far. I'll do this both in the numerator and the denominator. Oh, there's an integral missing here. Of course, there should be an integral down here as well. It's the same thing above and below. And now we actually use the Markov property. So here we have individual terms of conditional distributions of xj's on all the previous x's. And here we get to use this line up here that says if you have such a conditional, you can replace all the predecessors with just the immediate predecessor. So we do this in here. Can you see that this is blue? Yeah, so there are some terms to keep track of. Okay. I do the same thing in the denominator. And actually at the back here, I've now also added all the future states just as a reminder. Just a second. So that we could also predict everything that happens in the future. But because we have so far not considered any observations about them, they actually show up both in the numerator and the denominator, and so they just cancel out. We can just get rid of them, and they don't matter, right? If there's something that's going to happen in the future that is related to observations you haven't made yet, has no effect on your prediction. That's useful because it means we can think about an infinitely long time series into the future, and we never have to think about the stuff we haven't seen yet. Your question?
Just that for the denominator, shouldn't the index be j 2t, not less than t?
Here?
In the denominator, so the numerator doesn't.
You mean there should be an equal to t? Let's keep going and see. It might be that it should be an equal to t. Okay, let's see. Let's keep track and see whether we need to amend the notation at the end of the derivation. So now what's the next thing I do? Okay, I get rid of the green stuff, right? So we don't need to think about the future to reason about the past. That's convenient. And it only works because of the Markov property. Now we're left with this expression, which I just copied over. And now we need to look at the integral. So we are thinking about xt. So we care about terms that involve xt. And then there are all the other terms that don't involve xt. And here in the numerator, there's only one such term. It's this one. And all the other ones do not involve any x of xt. So we'll take this black stuff to the front and turn that into a single integral over time t minus 1. And now let's see. I didn't do this down here, but I did it all the way down here. I think the mistake is maybe up here, that I should have set this like all the way up to xt minus 1. Like here, and then this would be fine, right? Then we're down here again. So the problem is actually up here, that I'm not saying where to do the integral. So I mean this integral. And maybe that's clearer. And now we're left with the blue stuff in the numerator and the denominator. So there's only one integral down here, and then there's lots of integrals left. But at the bottom, the integral goes all the way to below t. But in the numerator, it goes to t minus 1. And so we see that these expressions here are the same in the numerator and the denominator. So all the integrals where j is less than t minus 1 just cancel. There's the same stuff in the numerator and the denominator, and so they go. But there's only one integral left, which is an integral over t minus 1, where the integral over dx t minus 2 still cancels, does it? Let's see, t minus 1, so add that t minus 1. Oh, yes, okay. Huh? Does anyone see it, the green bit? Why does it look this way? Okay, it's because here I'm writing a conditional distribution. So this expression here, where there's an integral over the dxt t minus 1, but not over up to t minus 2 here, that is exactly this green distribution. So that's you split this up into a xt minus 1 with a pxt minus 1 in here, and you get a Bayes theorem, which gives you a conditional distribution for xt minus 1 given all the preceding y's. And so the point of all of this, which you need to stare at a bit after the lecture, I think, again, if you really want to understand it, is that we have now written this predictive distribution, which we clearly care about, like what we know at the moment given all the past, into two terms that are of a local nature. The first one, well, actually maybe the second one. So the second one is a connection to what we did before. This term looks a lot like this term, but everything is just shifted by, well, not everything, but the x is shifted by t minus 1. So it's not exactly the same thing as this here, because there is a t minus 1 here in the y as well, but it's almost, right? It's what we knew about the preceding state given all the preceding data. And then there's a connection between the preceding state and the new state. You could think of this as a gain, like how much, similar to the Gaussian model where we thought about the covariance, the interdependence between some stuff that we know about and some new stuff. Here it's not a covariance, but a more general structure, a conditional probability distribution for t given t minus 1. And then something that sort of we can connect to if we think backwards. And there's a question, then we'll take a break and make the connection.
Why recursion is not inverse? Because when we look at the equation on the left, it looks like the denominator will be larger than the numerator. So shouldn't it be?
You think you're saying this will be larger than this? Yeah. Well, larger than is okay, right? It's a probability distribution.
Basically, when we divide them, the only expression there is like t. So shouldn't it be just inverse of the probability?
So this will be a p of y up to t minus 1, right? Because we're integrating out all the other x's, which is the term you're looking for in Bayes' theorem. And this will be a p of y given all the x's up to t minus 1. And then we integrate out all the x's up to t minus 2. So we're left with a p of all the y's given comma all the x's up to t minus 1. So comma equal, which you can also think of as a likelihood for y up to t minus 1 given xt minus 1 times p of xt minus 1. And that's your Bayes' theorem. So that's exactly this distribution. Right? So joined over xt minus 1 and all the y's divided by marginal for all the y's is equal to conditional. Good. Okay, so we've almost made the connection because the green thing here and the black thing there aren't exactly once shifted yet. So we need to think about how to do this local update to get the t minus 1th data point in here so that we can think of something like xt minus 1 given y up to t minus 2. Then we've created a clear recursion, and we'll do that after the break. Okay? So we'll be back in 5 minutes from now. Okay. There was a good question during the break that I want to briefly also share with you, which is maybe just as a reminder, maybe I phrased this bit badly about this sort of interdependence. So maybe I should put this differently. So I spoke about Gaussian process models and parametric models and Markov models. Gaussian process models are full generality. Every function value depends on every other function value, and that's an expensive thing to do, but it's also a very powerful notion. You can model all possible pairwise interdependencies between function values. This type of model already has a finite capacity, there's a finite number of features, but those features are not associated with a ordered space. So these are good models for a setting in which you have an input space that is maybe higher dimensional than 1. It doesn't have an order, and there's a finite amount of stuff to learn that you just want to find out over time. And as you get more and more data, you'll eventually learn more and more about these parameters. But the amount of flexibility in the modeling of these parameters gets sort of stuck at some point. It saturates. The models we're talking about now are models in which we're living in a world that has an order, a one-dimensional space called time. So there is a past and a future. In high-dimensional spaces, functions that map from R2 to R, or R to the whatever, 768 to R, there is no past and future. If you're sitting in X space, you don't know which direction is past and future. But if you have a one-dimensional space, then there is a clear, unique separation into what comes before and after. And that's the structure we're making use of here now. And this is good for worlds in which the worlds keeps drifting, keeps changing over time, so that you'll always need some flexibility to learn some new stuff. You could also call this dataset shift, or continual learning, lifelong learning. All of these words are related to this idea, right? So what we've now found is this beautiful equation, even though the derivation was painful and ugly. This general structure in this abstract form is sometimes called the Chapman-Kolmogorov equation, at least in the sort of signal processing community. In the numerical community, it's also called the predict equation or the forward equation in the more computational side of things, in classic AI, where we are thinking of some information being passed along a graph. And these corresponding models that we're building here are then called predictor-corrector architectures, by the way, for those of you who have taken the numerics class. These are all the exact same ideas. They just use different lingo. And now we need to do a way to make this an actual recursion, we need to be able to shift t to t minus 1 here. And we haven't quite done that yet because we haven't shifted in y, basically. But that bit is easy. It's just a one-liner. It's just Bayes' theorem. So to get from xt given y all the way to t minus 1, so given our prediction for the current time given all the past data, and a new local observation, we just do Bayes' theorem. And this works because of the assumption that local data are only dependent on the local state. So to condition on a new datum, local datum, we observe the new datum, which only depends on our local state. We multiply with our local predictive for xt given all the past states. That's sort of today's prior, if you like, right? Today's prior with today's data point normalized by the evidence for this one single observation gives us tomorrow's prior, basically. The thing we can now shove into this recursion, and then we can go once forward to xt plus 1. So that's actually the entire structure we need to keep track of a stream of incoming data. And I could stop the lecture here, and we could move on to concrete model classes that do this. This is important to point out. However, there are sometimes also situations that, of course, you immediately ask for, where you have some future data. So you actually have a sequence of data that go from time 0 to all the way to time capital T. And then you want to make predictions for the states across time that take into account all of these data, both in the past and in the future. In such situations, there is an extra step that tells us how to get from the future back to the past. But before I do that, which is going to be the next slide, it's important to point out that we don't always have to do this. There are genuinely important settings where you only need to do this forward predict Chapman-Kolmogorov step, also called the filtering step. Why? Well, those settings are exactly the online settings, the online type situations, right? If you have a process that keeps running continuously in time, and there is new data coming in all the time, then you can't possibly, at any point in the future, always consider like a consistent state over all the past states, a consistent prediction over all the past states, because the stuff you would predict over would keep growing linearly with time. And so necessarily, however you represent this or these objects, there would be a super constant memory requirement, right? More than constant memory requirement. So in applications like online sensor readings, all the streaming online settings, this is all we need. And we don't need anything else. Is that clear? Question? This is a very good question. So is it true that we don't need to refine our past predictions? If you want to make a statement at time t about the past, if you want to say, what do I now believe the state was at time t minus 1, t minus 2, and so on, then you need to do something extra, which is what we're going to do on the next slide. But typically in online settings, you don't want that. You just don't care, right? I believed something yesterday. Now that I know more, I realize that I believed the wrong thing. But I don't care because it's today and not yesterday, right? So in such settings, you just ignore what you predicted in the past and you don't care about it anymore. But if you want to do this, if you want to revisit the past and sort of now make a refined, consistent statement that also takes into account things you found out later, you need to do an extra step. And that step is called smoothing. So that previous two steps were called filtering and updating, or predict and update, Chapman-Kolmogorov and Bayes' theorem. And here is a third equation that tells us how to get, let's look at the sort of the ends of the equation and not at the ugly bits. It tells us how to construct a prediction for the state at time t given all the data. So y now has no index, so it goes all the way from 0 to whatever the end of our time series was. Let's say n, right, or capital T or whatever. But not little t. It goes beyond little t. So to do that, we do the following thing. First of all, we're going to convince ourselves that, of course, we're going to need some kind of recursive structure again. And the trick is going to be that we only need to consider what we know now about the next state thanks to all the next data, all the future data. And that stuff that we know about the next state will be enough because of the Markov property. And that's going to give us some other type of recursion that we can then do the other way around. So to do that, we first reintroduce the next state, xt plus 1. And we can do this again using the product rule, the sum rule. So we just integrate it out, and then we can write it into our joint distribution. Then we use the product rule to write this joint distribution as a product of a probability distribution and a conditional distribution, a green and a blue bit. And now let's only look at this blue bit for a moment. We are going to revisit it later. We're going to revisit the green thing below. That green thing will show up down here again. Actually, maybe let's already think about this briefly. Why are we happy with this green thing? Because that's the recursive bit we're going to connect to, right? It's if you compare these two to each other, then they are exactly the kind of thing we need to do some kind of inductive reasoning, right? If you have p of xt plus 1 given all the y's, and we know how to get from 0 to t, then this is going to be the bit that tells us how to incorporate the future. So let's think about this blue stuff. So that's the predictive distribution for t given all the data and t plus 1. For that, I'm just going to copy this blue thing down here. And now we'll do a little bit of algebra. And given your reaction to the previous slide, I'm not sure if I should even do it, but I'm just going to highlight it very briefly. We're again using effectively Bayes' theorem, right? So this is a posterior over xt given all the y's and xt plus 1. So we're putting in all the y's, but we're actually splitting it up already because we can guess what's going to happen into a predictive distribution for future data given everything on the right. So the future state, the current state we care about, and all the past data times a prior conditioned on everything that we're also conditioning on here with a normalization constant below for Bayes' theorem. So it's just keeping track of variables the right way. And then in the denominator here, we realize that there are terms that don't depend on xt because of the Markov property. So here we have xt plus 1 in there. So therefore, xt can drop out of this term in the likelihood, and the integral goes over here. Now that the integral is over a probability distribution over xt, so it's just 1. So that drops out. This entire thing just drops out. We're left with this thing at the top. And now we see that these two terms actually cancel, right? The thing in the numerator and the denominator is exactly the same, so it's gone. And we're left with just this expression. So we've just realized that we can think about our predictive distribution at time t, given all the data and t plus 1 as previous data and t plus 1. So this is a separation into two sources of information. The future as represented by this finite object at time t plus 1, and the past, all the past data, but for that we already know how to deal with it. That's Chapman-Kolmogorov, predict, filtering, and so on. So let's take this expression and move it over here. That's the exact, this is an exact equal, so this equality here continues, basically. We just rewritten it now. And here we can again use Bayes' theorem, rewrite things. So basically not Bayes' theorem, it's the product rule, right? So here's a joint, here's a conditional, so we need to normalize. And then move in so this is a joint distribution over xt and xt plus 1, so we split that up again using the product rule. And now we get an expression that I have colored in a bit. So here we're using, again, Markov property. So p of xt plus 1 given xt and previous data doesn't depend on previous data, so it only depends on xt. So the yt is gone here. And now we're left with an interesting object. So this is the stuff we're going to plug in here, right? So remember that we're talking about the blue term from up here, so we can reintroduce this blue term down here. And we'll find that this predictive distribution for the state at time t, given all the data, is equal to, first of all, this red thing here, which doesn't depend on xt plus 1, so we can take it outside of the integral, which is the filtering distribution. So that's a thing we already have from the previous slide. Great. So we can just keep it. That's something we already know how to deal with. And then in this integral, we have the quantity that is sort of one step ahead in the induction at xt plus 1 given y. So that's our tail, the recursion tail. That's where we can continue the algorithm. and then a local term that only depends on sort of two terms that we can locally control. So this is something that we have from filtering, right? So this object we have computed from Chapman-Kolmogorov previously in filtering. And this is a thing that we get from the model, the Markov, the local Markov object, the Markov kernel, if you like, xt plus 1 given xt. And we can, like, they show up in a fraction, which basically tells us how much to care about the future when compared to the past. So here is how much information we get from everything so far, from the past. And here is how much this new stuff relates to us locally. And that tells us how much to take into account this recursion term coming in. And so with that, we have a whole algorithmic structure available that isn't concretely instantiated yet. It's not an actual algorithm you can implement yet on a Turing machine because it's just abstract nonsense effectively. But it tells us what the structure of the algorithm is going to be before we do the actual computations. So given a set of observations assumed to be generated by a changing latent state from a Markov chain with these local observation likelihoods and the Markov property for the dynamics of the state, the algorithm we need to implement has a structure that will give it complexity linear in time and in memory. Or actually, more precisely, if you only care about your local prediction at time t, and you don't care about what you predicted in the past, you actually get away with linear time, linear compute complexity, and constant space or memory complexity. So I'm mixing up a bit the nomenclature from theoretical computer science and machine learning, so it's a bit tricky. In computer science, we say time and space complexity, right? Where time is compute time and space is memory, length of the tape. Here, we have to be a bit careful because time now also is this thing that we're modeling our sequence over. So I'm going to call this linear in the number of steps the algorithm has taken, the number of time steps, when we talk about the computational cost, and constant in how much memory you have to keep around. So that's exactly what we want for online settings. You once say, I have this device that has a fixed amount of memory, and I will send this through time, and every time step it'll do a local thing that has constant complexity. So if I do this for t time steps, the overall thing will be of cost t. And what do I need to do? I need to implement these two steps. A predict step, that is a recursive type object. This is called the Chapman-Kolmogorov equation, or the filtering step. And then an update step. Actually, I mean, this whole thing together is called filtering, these two steps, predict and update. Prediction correction sequences. The first one is this fancy equation. The other one is just Bayes' theorem. These together are called filtering, this predict update step. And then afterwards, if I should have an endpoint at some point, if at some point in the future data stops arriving, and I have time to think about the past and revisit, reminisce about what I used to believe, and I want to update my beliefs now in hindsight, then I need to do this extra step called the backward pass or the smoothing step that, again, is a recursion, but now it's a recursion in the other direction. So it uses the objects that we have used during prediction and then corrects them with an extra term from the future. So to do this, we have to, of course, be able to access these red bits, they're also down here in the gain, from the past. So that means if we want to do something like this, we have to store these filtering distributions. And then memory complexity is suddenly also linear. Right? You have to keep a tail around an array of growing size that stores all these predictive distributions. And then you can do this kind of update. So here is a pseudo code that does this. So to do inference in a Markov chain, given that you have a finite Markov sequence, you do this forward loop that consists of predict and update until the end, and then you go backwards from the end to the front, reusing terms that you have computed in memory, so they're sort of still around here in a way to get a joint distribution. Okay, so that was a lot of abstract algorithms. And 2 years ago, I would have here made a switch and said, now let's build an actual algorithm. Like, let's do this. And that actual algorithm is called the Kalman filter. This year, we're going to do something slightly different. I'll do the Kalman filter on Thursday. Actually, the slides for it are already here as a backup, but I'll just do it on Thursday. And instead, I want to point out something that has literally emerged as a very interesting observation since then, in the last 2 years, more or less. I mean, not actually 2 years, a little bit more than that, but it took us some time to understand and realize, which is only for the excited computer scientists in the room who care about algorithms, because it actually turns out that these type of computations, they have an extra structure that allows us to do inference in sublinear time, assuming that we have parallel computation available. Who is excited about parallel computation? Half the room, right? So it's the machine learning people have like, oh, you need to know about GPUs. Like, what can I do with a GPU? Let's see. So, and to do this, I'm going to talk about a very concrete algorithm for a moment that seemingly has nothing to do with filtering so far, but then we'll make a connection and we'll discover that filtering is a generalization of this type of algorithm. And it's the following thing. So it couldn't be more basic. Imagine the following setup. Here's an algorithm that computes the sum of the elements of an array. Okay? So what I do in this piece of code is import some stuff. Then I make an array that contains random numbers, and it's of size 2 by n, where n is 10,000. Okay? Easy enough. That, of course, let's say someone just did that. That's my data set. And let's imagine my task is to compute the sum over this array along dimension, the long dimension, the 10,000 dimensional one, right? So I want to have a collapsed this array along this long line to a 2-dimensional array. Easy enough, right? So I also actually have fancy code for this. It's over here. Can you read this in the back? No. No? Good. So here it is. I create this fancy array, and then I do this. Yeah? So here I just sum over this array, and okay, so I do this in the most naive way possible. I write a Python for loop, and that just literally walks over these slices of the array and sums them up. This takes 416 milliseconds to do this for 10,000 elements in the array. Half a second. Okay. So you are already going, yeah, okay, but there are actually underlying there are like, you know, nice routines in NumPy and Jack's NumPy that do this for you, and they're much, much faster. Yeah, let's think about them for a second, because we want to generalize them, right? So of course I could just call y.sum, but that's not going to generalize, right? I want to think about how to do this with a more general data structure. So the next thing you could now do is to realize that I can rewrite this operation, this here, as a local thing, right? Because what's happening here, if I look at this line here, you see that it only involves the index I-1 and I. Right? So there's some kind of local operation happening. Okay? So I could fancily rewrite this, saying I'm defining the operator. That operator is a lambda function that depends on 2 objects. The first one is traditionally called the carry. It's the thing that it carries along with it, right? And the second thing is the local element, I. Okay? And then I can write the exact same code that I did before with this operator. And that, of course, is not going to make anything faster. It just tells me what's happening here. So I did this actually in my code as well. Here we go. And you can see it's not making anything faster. If anything, it creates more overhead because I'm using this fancy lambda function. But now, the first thing I can do is I can use this operator structure to define to define this sort of, to tell Python, actually not Python, but JAX, or the underlying acceleration library LAX, that this is the thing I'm doing. It's a local operation. And that local operation is, in JAX, is called a scan. So there is a design pattern called scan that describes exactly this thing. So you're going through an array, you're doing a local computation. And this local computation, of course, means that we can speed up things a little bit, right? We can pre-compile effectively this for loop and move it outside of Python. So this is what this looks like in Python. So this bit is the same as before. We've defined this operator, which you've seen before. And I'm now just calling a nice routine in JAX called lex.scan. So lex is this linear algebra accelerator in JAX. And I'm just telling it to do this map reduction, effectively. So what I'm doing here is really just a way of getting around Python. So this exact line is just a way to tell JAX that it's supposed to do a for loop with this local structure, and please don't call Python, right? So I'll do that here. This is this line. And now I'm down to 23 milliseconds from 423. Okay, who knew of scan operations before? People who have taken some functional program. Okay, not so much distributed computing. Good. So it's worth doing this. Great. Cool. So there's this thing called scan, and it's really just, the thing we're doing here is literally just Python for loops are super inefficient because it's an interpreted language. So we're doing a little bit of extra work to tell JAX about this local structure, this operator, this scan operator, and then that allows us to call a much more efficient library that's written in C, or C++, I think, actually, to do this for loop faster. Okay, fine. But it's not mathematically interesting. It's just engineering. But you can do that for yourself. Now, here comes an interesting thing. Notice that this addition is associative. So what we're doing here is we're computing plus, right? We're computing a sum of an array. Huh? And plus is an associative operation, as you all know from your, high school. And that associative structure is actually a super powerful aspect, a super powerful idea that allows for parallelization in a non-embarrassing way. So this operation is clearly not embarrassingly parallel, right? To sum over an array, you can't just do something purely local for every single element of the array, because you have to somehow keep track of the stuff you've summed up, right? But it's maybe the most basic non-embarrassingly parallel problem. And there's an algorithm for it that runs much faster than this scan that is due to two guys called Hillis and Steele from 1986. This is a link to the paper. You can read it. It's very nice. It's one of these classic computer science papers with lots of cool ideas. And it looks like this, and it's called an associative scan. Sometimes these structures are also called a prefix-sum, because we're doing a sum with a prefix, the carry that we carry along. And the algorithm looks like this. It's not exactly easy to understand what it does if you just look at this equation. So there's a picture from the original paper that I literally copied out. So the idea is that imagine you have hardware that can do many things in parallel. Let's assume we have enough threads available that we can have one thread for every element in the array. That's just for theoretical assumptions. That makes it easier to think about. Then what we can do is we can do a parallel pass initially that does these local pairwise sums all at once in parallel. And then we know that we have half of the summons already locally collected, right? And now we only have half as many things that we need to sum up. Then we go in parallel through these half as many things and always take the one more bit to it that we haven't added yet, which you can do in parallel again with the same number of threads. Do that again and again, and after logarithmically many steps in the size of the array, we have all the sums together. So in particular here at the end, we now have the correct sum over everything. That algorithm, therefore, has runtime complexity O of log n, where n is the length of the array, assuming that you have arbitrarily many threads available. And JAX, conveniently enough, because it's written by people who care about this, has actually a pattern for this called an associative scan, which we can call, and I do this in my call here, with this add operator, and you can see it runs again about 20 times or 15 times faster than the normal scan, using a bunch of threads on this little machine here, which doesn't even have a GPU, but yeah. And so what do I need to do extra? Nothing, actually. I just inform JAX that the operator I give to it is associative. That's the only thing, right? I need to do the exact same code. I just need to make sure that this operator is associative, because if it isn't, then I can't do this arbitrary reordering of how I connect things together, and then everything breaks apart. So what does this all have to do with the stuff we've been doing today? Well, sorry. So remember this picture that I showed before? This is exactly just summing up stuff, right? It's just going through and locally adding one thing. And after t time steps, we just have a sum of random numbers. So this, of course, is only one example. And this particular algorithm that I've now carefully constructed here doesn't necessarily look like a sum anymore, right? And actually, it isn't. It's not a sum. It's a more general thing to do. But it happens to be associative as well. And that's totally non-obvious to see. It's not something you can just squint your eyes and say, oh, OK, that's associative. No, no. You have to have a theorem for it. And that theorem was published in 2019, so a little bit more than 2 years ago. But it took me some time to understand what's going on. And we ended up writing a paper together with Simo Säke, the guy who came up with it. He's a colleague in Finland who is basically the Pope of filtering, knows all about it. And he had this beautiful insight, which I'm just excited about, so I'm going to tell you about it, and then we're done, which is that it turns out there is a way to write the Chapman-Kolmogorov equation, this filtering step, as an operation that is associative. But to do that, we need to construct an operation that is actually associative. And it's not the notation we've encountered so far. It's related to it. And he managed to rearrange it such that it works. So he says, first of all, consider a sequence of pairs of conditionals and likelihoods. So that's going to be the sequence, the array over which our associative scan is going to operate. And that sequence, so we basically need to think about what the thing is that we're summing over, right? Or not summing, but doing the associative operation over. And it happens to be this sequence, which abstractly we're going to write like this. So it's a sequence of tuples, pairs, of two functions. One bivariate function, f, at time t, and one univariate function, gt, at time t, which is concretely instantiated for our Bayesian filtering problem by this conditional distribution. So that's the conditional distribution for xt given yt and xt minus 1. That's an equation, a conditional distribution that we didn't have on the previous slides. But it's one that you can easily enough construct from the ones that we had on previous slides. And this thing down here is a conditional distribution for the local yt given xt minus 1, actually, which is a bit weird. It's sort of once removed from the stuff that we've used in the previous slides. But again, it's just more fancy rearranging of equations. And then the second thing we need, second ingredient, is this associative operator. So that turns out to be this operator. So it's an operation that operates on pairs of these tuples that does the following computation. So it actually does something. It produces a new tuple. Right? It maps from a pair of tuples to a new tuple. That's, of course, what our associative operator has to do. A tuple of a pair of a bivariate function and a univariate function, which happen to look like this. And now they are really so separate, different from each other that, like, so, no, not so different, so opaque that you just have to believe me that that's the case. And it turns out, and that's a theorem that you can read up in this paper, if you apply this operator to this sequence of pairs. First of all, that operation is associative, which is completely not obvious. You have to write a proof to show that this is the case. And secondly, the sequence, like if you do this associative scan on this sequence of states, then the output of this associative scan running up to time t is true distributions that you care about. The first one is your your filtering distribution, P of xt given all the previous data, including the local one. And actually also an interesting thing, which is the evidence for your data set so far. Why is this cool? Well, it's only cool if you're a computer scientist and you care about complexity of algorithms. What this means is you can compute the filtering distribution in sublinear time if you have parallel computing available. So you can actually catch up with the future. You can travel into the future if you like, right? You can have a sequence of numbers arriving, and then you can sort of say, like, you more or less instantly in logarithmic time catch up with them if you're allowed to use parallel computation. And the pattern to use for this is this associative scan. This is called parallel in time filtering, and it's really a new thing. It arrived in 2019, and people are still digesting what this actually means for online learning, for example. Quick question? Well, it's sort of, so the question is this applicable in the online setting? It's sort of super applicable, right? It's even better than online. So that means I can tell you, you go to sleep at night, you sleep for 8 hours, and data keeps accumulating during that time. And actually, you only have enough compute resources to just about keep track of stuff in linear time. Then you can wake up in the morning and say, oh, if only I have 2 threads available, then I can speed up the computation. I can be basically twice as fast and catch up in my 8 hours, the 8 hours that I've slept. Or if I have 3 threads available, I now only need to work for 4 hours. If I have an arbitrary number of threads available, I can do in logarithmic time, which I would otherwise have to do in linear time. Okay, so how is this relevant for the online setting? I think what I just constructed is a bit, not so sure. This setting is particularly relevant, and now I'm gonna shamelessly advertise our own work with Simo, in settings where this time aspect is a simulated time. So let's say you want to solve a partial differential equation across time. You want to simulate something that's going to happen in the future. It depends on time, or that something you simulate, the climate, for example, right? Then you can speed up the computation a lot, up to exponentially, right, down from linear to logarithmic, if you only have enough threads available. And so that is not necessarily the online setting. It's more like, if you want to look into the future, basically, you can look exponentially far into the future if you only have unbounded compute resources available. I'm gonna, on Thursday, I'm gonna tell you how to turn all of this nonsense into an actual algorithm. We'll do that then, and you'll get homework to also build these, even maybe using associative scans. I'm gonna close now and say, what was the point of today? It was a very abstract lecture, I realized. On Thursday, it's gonna be all very concrete. We discovered that for data structures that arrive as a sequence in time, there is a particular algorithmic structure, a design pattern called filtering, prediction update, and smoothing that requires an assumption about conditional independence called the Markov property and yields a concrete class of algorithms called Bayesian filters and smoothers, of which Kalman filters are a concrete linear Gaussian instantiation that allow us to do online inference with constant memory requirements and constant compute cost per step, which means linear compute cost to process a fixed amount of data. In fact, there is a beautiful underlying structure due to the associativity of the associated operations that even allow parallelism to speed up the computation in a superlinear fashion. I hope that some of you enjoyed all of these abstract insights, and on Thursday we'll build an actual algorithm. Thank you.